thank you very much. So this is joint work with our compiler design lab here in Saarbrücken and the graphics lab also in Saarbrücken and the German Research Center for Artificial Intelligence. So let's have a brief look about intermediate representations we are currently using today in order to compile programs. So on the one hand, we have typical imperative languages like C or Fortran, and we're using instruction lists, control flow graphs, and nowadays SSA form based representation and doing optimizations on that. Now there's this more progressive idea of having the sea of nodes where you don't have these rather rigid instruction lists anymore, but instead you have all those computations, you maintain them in a graph. So for instance, the Java hotspot compiler uses this sort of representation, or LLVM, or also the new Google compiler, the JavaScript compiler Turbofan. On the other hand, you have functional languages like Haskell or ML, and the intermediate representation those guys are using under the hood are more inspired by the lambda calculus. For instance, the Glasgow Haskell compiler uses this language called Core, or Camel has this lambda IR, and also an idea which goes as far back as into the late 70s is using continuation parsing style. We'll get to that in a minute. But first, let's have a look at how modern languages like C++11 also make use of higher order functions. So as a motivating example, let's have a look at how we implement a post-order visit in a binary tree. So here we have a node in a binary tree, and we have some data in this node. We have a left child, we have a right child. And now we want to do a post-order visit in this tree, so passing a pointer to this node, to this function. We check if the left child is there, we recurse to the left child. If the right child is there, we recurse into the right child. And let's say we want to print all those nodes in post order, so we are dumping the node. So now let's say we're doing lots of those post order iterations, and then we have basically two choices which we can use to factor out this visiting algorithm. So one choice would be using C++ iterators. But first of all, even if you have a rather simple iteration algorithm, it's actually quite hard to come up with a standard conforming iterator which works well with the STL and so forth. And even if you do that right, it's really hard to get this algorithm into this iterator. So either you're using additional pointers in this node data structure, but then you actually don't implement this algorithm we had before, or you somehow have to come up with this recursion stack in this iterator. So what you will need is like some explicitly managed heap on this explicit heap managed stack. Doesn't sound terribly efficient to me. Another option would be using higher order function. So let's have a look how this might work out. So here we have the post order visit again, and we now install another parameter f, which is a function, returns nothing, but it yields the data value to the whoever's using this function. So here's the here's the call to this function f, and we are just propagate this data of this node to f. So now now that we have factored out this visiting algorithm, we can just invoke post order visit, pass a closure to that thing, and dump the data in the node. Here's another use case. We can say sum up all data in the tree. Here we have the variable result. Here we have the post order visit, and note that we are capturing the result variable here as a free variable in the closure, and then we dump out the result. Okay, so let's see what Clang is doing with this program. So just the post order visit and the print, and I compiled with O3 and also with F no exceptions, because exception handling is known to clutter the IR and hinder other optimizations from kicking in. So this is what you get. This is just the post order visit, and this is the print function. Okay, so at that point, we thought maybe LLVM is not the right tool. It's too low level to actually optimize stuff like that. So we stepped a little bit back and thought maybe it's a good idea to have like another layer upon LLVM and do optimizations with higher order functions on that thing. So if you're interested in the work I'm talking today about, is published in the graph-based higher order intermediate representation on the CGO. We're also doing other optimizations where it's really handy to have higher order functions in the IRR in the first place. For instance, we are doing partial evaluation of higher order functions. Just another use case where this is useful for us. Okay, but now let's have a look about what LLVM and Clang actually is doing, why this code looks so cluttered. So here we have another higher order function, range. And this range function ranges from A to B, and we have this function f, which we are using to propagate this ranged values to. We are invoking this function here with the current value of A, and here we recurse. And note that because it's a recursive implementation, we are passing f again to range. Here we have the user of this function range, and we are also having a closure here. We are invoking some use, and we are propagating this value n to that. So n is a free variable here. So let's see what Clang is essentially doing. So first of all, we need this closure base structure, which is a function pointer. So this is shared for all f's, so to say. Then we have the actual closure, which is used inside foo. So this is the closure base. And this is the n, the free variable here. Then this is this lambda function. This is the actual thing which uses this function use. Then we have some weird pointer casts over there to actually get the data here. This is the actual function range, where we equip the range function with a pointer to that closure. Some weird casts again. And here we have the actual function foo, where we pack this closure and pass that to range. So this is what Clang doing, and this is why everything looks so cluttered. So what does LLVM do in order to get rid of closures? So LLVM tries to inline the closure's function pointer and then SSA construct all those structs and free variables using mem-to-rec scalar replacements of aggregates. And this works well for typical STL algorithms. But if you have higher order recursive functions like the range function or the post order visit I had in the introduction, it doesn't turn out to work that well. So again, Clang compiles to an abstract syntax tree. And on that level, the closure conversion already happens, goes down to LLVM and then to the backend. And as we've seen, the closure conversion already implements higher order functions at that level. So the IR is significantly bloated and tainted with the implementation of higher order functions. So it's really difficult to get the information back of what's actually happening there. So what we are doing in our research language Impala, we are compiling to an AST, and we don't do the closure conversion there. Instead, we are compiling to our higher order intermediate representation called Thorin. There we're doing a bunch of optimization, including a powerful closure elimination phase I will talk about in a minute. And after we are done with that, we're going down to LLVM. So let's have a look how the intermediate representation looks like. First, a small recap how SSA form looks like. So here we have like a familiar if diamond, which either selects for the variable a 23 or 42, depending on the condition of n. So here we have this in SSA form, where we have this phi function, which does the select in the next block. And I told you earlier that for functional people, there's this thing called continuation parsing style. And let's compare SSA form to continuation parsing style. So on the left-hand side, we have SSA form. On the right-hand side, there's continuation parsing style. It actually doesn't look too different, but the key thing here about continuation parsing style is we have a bunch of functions, and those functions don't return. So this is why the return value, the return type is bottom. And we have to nest all functions in order to use things which are defined outside. So for instance, we have in this branch, we're using n, which is actually defined as parameter in foo, so we have to nest everything. We don't have to do this in SSA form like in LLVM. So this is where our idea kicks in. We do not like this enforcing of this nesting. So what we did is we just get rid of that. So we have like a graph-based representation, and we just have a bunch of those continuations. And there are actually just three concepts. So we have primobs, so like this n equals 0. We have parameters, and we have continuations. And all those three things are just linked in a graph, and that's it. Okay, so let's compare Thorin to classic continuation parsing style. So what you're doing in a classic continuation parsing style, you have let and letrec to nest functions which might be recursive in the case of letrec. So this is just in our case a graph edge which is either acyclic or cyclic in the case of recursion. Then you have this block nesting, which is implicit in Thorin because we don't have this block nesting. Name resolution just as a graph edge, and this name capture thing, which usually happens for functional representations, doesn't happen for us because names are just an edge in the graph. Let's compare this to SSA form. So as I mentioned earlier, we just have this notion of continuations. We have parameters, and we have calls. So in SSA form, each function is just a continuation in our case. Basic blocks are also just continuations. Parameters are parameters. Then we have this phi function here in the SSA form, and the phi function is also just a parameter, as you can see in the next continuation on the right-hand side. Then we have terminators, as known in LLVM, which end the basic block, and those terminators are just calls in continuation parsing style. And note that the arguments of the phi, the 23 and the 42, are actually just arguments to the for calling the continuation next. And we have primobs, which resemble instructions in LLVM, or basically in SSA form. So let's have a look at a bunch of optimizations we are doing. And the first thing you probably would note is that those two representations, putting a little bit syntax aside, basically look the same. And to be more precise, we're talking about control flow form, which, putting syntax aside, is the same. So we have those first order continuations, which means these are continuations which don't receive any higher order arguments as arguments. So these are basic blocks, like then, else, and next. And all top-level continuations where we have this one higher order argument, this return, is a function. And this is pretty straightforward to translate from the left-hand side to the right-hand side, or vice versa. And if we have a program which is in this control flow form, we don't need any closures. Okay, so that's nice. But what about programs which are not in control flow form? So here we have, again, this higher order function range. We have this function f, this additional parameter here. Here's the recursive call. And this is how this looks like in continuation passing style. So we have this f here and this red continuation over there. So this is, so we have more than just like one return. So this is not in control flow form, but we can convert this to control flow form. And we can do this if either the program is recursion free or uses tail recursion. Okay, so there are several classes of programs we identify. So we have this control flow form, which is more or less straightforward, translatable to SSA form. Then we have this CFF control flow form convertible programs. And then there's this class of programs which are not even control flow convertible, and there we need explicit closures. And what we do in order to get from this CFF convertible programs to the programs in control flow form, we're using a technique called lambda mangling. Now, lambda mangling in a nutshell is similar to partial inlining, partial outlining. And because we do not differentiate between functions and basic blocks, you can also clone basic blocks, functions, or do some other interesting optimizations like loop healing or loop unrolling, because a loop is just a call of a continuation. You can just specialize the call to that loop or the call inside the loop. There's a little bit more to this lambda mangling technique, so I'm not going into details, but you can also do things like tail recursion elimination. And this is all we need in order to get rid of those closures for this CFF convertible programs. So let's briefly discuss our Leißa research language, Impala. So here again is the post order visit in our research language. Here we have a pointer to the node in a binary tree. Here we have the function f, which gets an integer and returns void. Here we have the recursive call if the left child exists. Here we have the recursive call if the right child exists. And here we have the function print, which gets a closure. We're receiving the data D in this node and can print this. And because such patterns are so common, we are using this nice for syntax. So this is just syntactic sugar to make it more readable. Here's another example. This is the sum we had earlier. So here we have this mutable variable result. We are adding up all the stuff inside the closure here and dumping the result. Now, a common complaint about this sort of programming with higher order functions is that you somehow lose this imperative style control flow. So probably you've noticed that if you're using C++ and the STL with standard functions or something, you will notice that you sort of get the effect of continue by just returning in this closure if some condition holds. So what we are doing when we're using our for syntax is that the return is actually the continue, which is more along the lines of how you're used to program stuff. And both return and continue are also just functions which you have to invoke or you can pass around. This is why we need this extra pair of parentheses to make this a function call. There's this thing you cannot do in C++ to just break out of this whole thing out. So break is an implicit continuation which points to the point of the loop after all this stuff happens. So you can use this to break off this whole iteration. So I mentioned earlier that programs are convertible to control flow form if everything is tail recursive, but now the post order visit isn't exactly tail recursive. But we have one degree of freedom, so to say, because top level functions are allowed to have one return continuation. So actually we just have to get rid of this function f, which is used here in this recursive call, and here in this recursive call. So let's have a look how this looks in the compiled LLVM. So here we have the post-order visit. So this is after we are completely done with that and generating LLVM. This is the whole program after compiling. So what remains is this function post-order visit, which just receives a pointer to this node data structure. Here we're comparing the left-hand side with null. If it's not null, we recurse to the left-hand child. Here we are doing the same on the right-hand side of the node. And we recurse to the right-hand side. And after that, so this is the interesting part, this is everything what remains from the closure. We are done. We just load the value and print it. That's it. So this is the whole program after we've done compiling it. Another thing what we have done in order to compare our representation, our technique of compilation with a more traditional approach is we've re-implemented a bunch of benchmarks from the computer language benchmark game to Impala and compared the runtime from the original C version. And you can see that pretty much it's more or less the same. There are some peaks on the left or the right-hand side, but I think it's fair to say that it's more or less the same. So the takeaway from these numbers and from these slides is that it doesn't hurt to have a higher order representation. As long as you don't do crazy stuff, you do not pay for that. But if you do crazy stuff, for instance, like this post-order visit, there's a good chance that we can get rid of that. And here we have all closures. By the way, all closures we used here have been removed by the Impala compiler. So as a summary, what have we seen today? We have seen this higher order intermediate representation we're using to optimize and compile higher order programs before going down to LLVM. We've seen that although we are more expressive in the sense that we can directly express higher order functions in the first place, there are actually less concepts. So they are just continuations, there are parameters, there are calls, and that's it. And we have seen that there's control flow form, which is putting syntax aside, is more or less the same as SSA form. It's straightforward to go from this representation to SSA form. There's this class of CFF convertible programs where we can also get rid of all those closures. And there's this bigger class of crazy programs where you need explicit closures. And that's it. Thank you.
So I have too many questions, so maybe we should have lunch. But
yeah.
The question is, the example I've seen so far in this talk or in the paper, it had only one prim of per basic block or per function. So what multiple primos?
So basically, each continuation is floating around in this graph, and you can have a whole bunch of primobs. And all those primobs are also floating around in this graph. At some point, we have a scheduler which decides, okay, well, here we have a bunch of primobs, and the scheduler decides, okay, this primob has to go there, and this primob has to go there. But for most optimizations we are doing, we actually do not care where this primob is scheduled. So if you have something like a plus b, we don't care whether this a plus b belongs to this continuation or that continuation. We simply don't care. There are just a few instances, especially later on when we are going down to LLVM, where we have to decide on that. And we have one phase which does that.
What distribution the code within them fell into these different categories?
Okay, so I get like basically the question is, so what's the distribution of those different classes of programs? So we
if we did something really cool with these CFF convertible ones, how frequently will we actually encounter those? How impactful would that be?
So we've not yet like done a user study where we actually counted the function. As I mentioned earlier, for typical stuff you're using when using the standard template library, this is easily convertible already by LVM without doing more magic. But I guess like now that we have C++11 and Lambda functions and closures are there, people are going to use more and more stuff of that. But we have not counted like how many use cases are there. But we've seen in our project, because we can get rid of all those closures and whatnot, so our users are using those features. So I guess like if it's there and it's fast, users will come.
So one thing just to point out, we don't get rid of all of the STL lambdas easily in LLVM.
Yeah, so there's much to doing it. So I tried to do that on one slide. There are a couple of fine-tuned phases which have to be in that order with these heuristics, and then if the star constellation is right, you get them right. You can get rid of them.
Why I am actually very interested in actually like teaching clang and LLVM to do more semantically aware transformations like this.
Yeah.
Be much more reliable.
Did you experience further optimization opportunities because of this, or the performance was more like just because we removed a lot of code?
I think that's a little bit hard to tell. I mean, in the sense of classic compilation, if you have your programs which are not higher order in the first place, it's basically the same game. If you do have higher order programs, I think you gain much. But it depends on the use cases. So as discussed earlier, if you have like a use case where LLVM can get rid of that, it's fine. If not, you've seen the code, it's getting slow.
Any other questions? Okay, let's thank Roland again.
Thank you very much.